Yep.
Good afternoon and welcome to Vanitec Presents Think Turf on Vanadium for High Street Strength Steel 2023, powered by Pro MFG Media. Our knowledge partners for this important virtual event are Technova and the Advanced Manufacturing Technology Development Center, IIT Madras. In today's session, industry experts will enlighten us on the following points: transformative role of vanadium in high-strength steel, latest global trends in the production, properties, and use of vanadium-containing steels, comprehensive understanding of vanadium's current application and future potential. Now, I would like to invite Dr. David Crother, technical consultant for Vanitec, for setting the context of today's webinar. Before that, I would like to give a brief introduction about Dr. Crother. He's graduated with a BA in Natural Science from the University of Cambridge, UK, and subsequently a PhD from the City University, London, UK. He has over 30 years of experience working in the steel industry in research and development with a focus on new product development, particularly flat products and high-strength microalloyed steels. At Vanitec, he is responsible for organizing and monitoring the Vanitec Research Program, which seeks to demonstrate new applications of vanadium in steel. Over to you, Dr. Crother.
Thank you very much for that introduction, and I'd like to welcome you all on behalf of Vanitec to this seminar this afternoon. Thank you very much for attending. I've got a short presentation which I'd like to show you all, which hopefully will act as an introduction to the rest of the session. So I'll just share my screen. I'll just go back a slide or two. Okay, is that all right? Can everyone see that?
Yes.
Okay. As I said, it's just a short presentation. I hope it'll set the scene for the rest of the afternoon. I hope to tell you something a little bit about the vanadium industry and also about vanadium's use in steel, just as an introduction to the rest of the afternoon. First of all, just an introduction to my organization, Vanitec. That's our mission statement, and really we're a trade association and we aim to promote the use of vanadium in steel and in other uses all around the world. So the Vanitec members are basically all the world's major vanadium producers, and they contribute to central funding, which we use to promote the use of vanadium around the world. Just looking at where vanadium is produced and where it's found, this is an indication of the world vanadium resources and vanadium reserves. And you can see that we've got about 63 million tons of resources, 20 million tons of reserves, and you can see that the reserves are quite widely distributed geographically. So China, Russia, South Africa are the major producers at the moment. There is a lot of activity in Australia, and we expect to see Australia starting to produce a lot shortly. I've not included India on this, although reserves have been identified in India, but at the moment there's no major vanadium production in India. Looking at trends in vanadium production, this shows vanadium production over the last 20 years or so, and you can see we've had a continual increase. A lot of this has been driven by China, and in particular the steel industry in China, which is a huge user of vanadium. I should apologize, this slide is slightly out of date. It only goes up to 2020. For 2022, world vanadium production is around about 120,000 tons, and we expect to see that increase continuing. Looking at vanadium applications, on the left-hand chart, you can see that the vast majority of vanadium, around about 90%, is used as an alloy element in steel, which is the topic of our webinar this afternoon. Some vanadium is used in titanium alloys, some is used as special chemicals and catalysts, and a small proportion is used as energy storage. Now, this relates to something called vanadium flow batteries, which are becoming very relevant in the drive to a zero carbon economy. And again, we see the energy storage sector, we think that's going to increase rapidly over the next few years. Looking at the use of vanadium in steel, the majority is used in HSLA steels, high strength, low alloy steels, and we're talking about vanadium additions of perhaps 0.1% or less or slightly more. Another proportion of vanadium goes into more highly alloyed steels, such as tool steels. And in these steels, we're talking about vanadium additions of perhaps 1 or 2%. Moving on to vanadium steel metallurgy now, and again, it's a huge topic, and we'll pick up on the details later on in the talk. But just as an introduction, I'd like to highlight some of the roles that vanadium plays in steel metallurgy. Vanadium can be present in solid solution, in which case it increases the hardenability of the steel, but it's often present as precipitates of vanadium carbides, vanadium nitrides, vanadium carbonitrides, and it's these precipitates which have a big influence on properties. They can be present in very large precipitates, for example, in tool steels, where they give wear resistance. The smaller precipitates can give precipitation strengthening, grain refinement, and other beneficial properties. And it's very much that the size and volume fraction of these precipitates that influence the steel properties. Looking at these precipitates in a little more detail, this just illustrates that the types of precipitates you can get. And in the top two pictures, we can see a random distribution of precipitates, and you can see some nice interactions of precipitates and dislocations. On the right-hand side, you can see a much denser precipitate distribution, and this is due to the high nitrogen content. And you'll often see vanadium used in combination with high nitrogen. In the bottom, we can see rows of vanadium precipitates, and this is known as interphase precipitates, and again, a common type of vanadium precipitate distribution. On the right-hand side, and perhaps not so well known, is that you can get precipitation in pearlitic ferrite. So here we have the dark bands are the cementite in pearlite, and in between we have vanadium precipitates in ferrite. So the vanadium precipitates can harden the pearlite as well as the ferrite. Vanadium precipitates can also act as nucleation sites for ferrite, and hence refine the grain size. On the left, we have a sort of composite precipitate with manganese sulfide and vanadium nitride, and a ferrite grain nucleating here. On the right, you can again see a vanadium nitride precipitate with 4 ferrite grains nucleating around it. And again, this shows that vanadium precipitates can refine the grain size, which is great for increasing both strength and toughness. Looking at some applications now, steel is used in the construction industry very widely, and that accounts for perhaps 50% of the steel of world steel production. And vanadium is used in a lot of these steel products. For example, in high-strength reinforcing bar, vanadium is very commonly used, particularly in China, where most of the rebar is vanadium containing, and also in the US. Vanadium is also used in high-strength sections, for example, and also in high-strength rods, which are drawn into wire to form suspension cables on bridges. Looking at the transportation sector, again, a major steel using sector, and vanadium microalloyed steel plates are often used in the shipbuilding industry. Vanadium is also used quite commonly in rails, and I think this has some relevance to the Indian situation, where, as I'm sure you know, there's a big expansion of the high-speed rail network, and vanadium containing rails are being used in this expansion because vanadium rails have increased wear resistance. Looking at the automotive sector, again, a big user of vanadium. Vanadium is used in components such as crankshafts and conrods, which are forged components, and vanadium can be used in an air-forged component. Vanadium is also used in wire rods for things like coils, and it's also used in cold rolled strips, which are used in the body of the car. Moving away now from steel metallurgy, I'd like to give a few slides related to India. This slide here shows the steel production in India. This is the blue line here. And as I'm sure we know, India is now the world's second largest steel producer, producing over 120 million tons of steel. And it has big ambitions to increase this steel production over the coming years. And this is this blue dotted line. The vanadium consumption in India is the orange line, and again you can see a general increase in vanadium consumption, which matches the steel production. The grey line is what we call the specific vanadium consumption, and this is the average amount of vanadium used in every ton of steel. So as we move to using more high strength steels, we expect to see more vanadium used. And you can see that again, this line is trending upwards, showing that more high strength steels containing vanadium are being used. At the moment, India has quite a low value for this specific vanadium consumption compared with the world average. And that means that perhaps India is using less high strength steels containing vanadium than the rest of the world. Again, that means India has great potential for vanadium containing HSLA steels. I'd like to draw attention to one of the other things that Vanitec does in India. Part of my job is to develop a research program for Vanitec, and we've got two projects ongoing in India at the moment. I say two, that the first one is just finished. And I'm glad to say we have representatives from both of these projects on the panel today, Dr. Chakrabarty and Dr. Patra. I should say that Vanitec is always keen to support and promote research developing high-strength steels. So if anyone has any suggestions for new research projects on vanadium-containing steels, if you could please get in touch, and we'd be very interested in taking a look at any new ideas. We're also keen to promote the use of vanadium microalloyed steels, which is the purpose of this seminar. And we've also held other seminars, particularly one last year, again with the help of some of our research associates. And we held a great seminar on microalloyed steels, which again aims to promote the use of these steels. I'd like to finish off by, again, if you have any questions or queries, you're welcome to get in touch with me directly, or I'd encourage you to have a look at the Vanitec website, which will give you more information on the sorts of things we do, and also a lot of information on the use of vanadium in general. So that brings me to the end of my presentation. Thank you very much for your attention, and I'm sure during the next hour or so we will have plenty of time for discussions and questions. So again, thank you very much.
Thank you, Dr. Crawford. Now we would begin with the much awaited panel discussion. But before that, I would like to tell the audience that we have some exciting prizes, lucky draw, and as well as we have some interesting polls coming up. So stay tuned till the end of the webinar. So we would like to begin by introducing the panel speakers for our panel discussion on harnessing the strength, the pivotal role of vanadium in steel production and application. I would like to firstly introduce Dr. S. Sankaran, Professor Metallurgical and Materials Engineering from IIT Madras. Dr. Shankaran received his PhD from IIT Kanpur in 2004. Subsequently, he was postdoctorate research associate in the United States of Louisiana, USA till 2007 before joining IIT Madras. His research interests are in the field of deformation processing of materials, microstructure, mechanical behavior, correlations in structural materials, and transmission electron microscopy. A warm welcome, Professor Sankaran, and thank you so much for joining us today.
Thank you very much. Yeah.
Our next panelist is Dr. Debalay Chakrabarti, Professor, Metallurgy and Material Engineering, IIT Kharagpur, with an MTech from IIT Kharagpur and PhD from the University, UK. Dr. Debalay Chakrabarti has also worked as a researcher in Sweden Technology Centre, Rotherham, for Chorus Steel in the UK. His research areas include steel product development, microstructural engineering, and structure properties relationship in metallic alloys. Dr. Chakrabarti won the Metallurgist of the Year award in 2019 in the ferrous category. So a very warm welcome, sir, and thank you so much for joining us today.
Thank you very much for the opportunity.
Our pleasure, sir. Our next panel speaker is Mr. Senthil Kumar Varatharajan, Head of Material Technology, Mahindra & Mahindra. With over 23 years of experience, Mr. Varatharajan comes with multidisciplinary expertise in the field of automotive materials, fatigue and component validation, regulatory frameworks, new technology development, and circularity initiatives. His innovation track record includes 30 plus IPRs. He is also a technology specialist in the field of nanofluids, functional nanomaterials, fuels, as well as automotive lightweight technology. A very warm welcome, sir, and pleasure having you on the panel.
Thank you. Thank you so much for having me here today. Thank you.
Our next speaker is Dr. Sudipta Patra, Assistant Professor, Metallurgical Engineering from IIT BHU Varanasi. With more than 7 years in the steel industry, this young metallurgist has already presented 25 papers in international journals and has made 10 presentations at global conferences. Winner of the Young Metallurgist of the Year award, Dr. Patra specializes in high-strength steel, toughness steel, physical metallurgy of steel and stainless steel, thermomechanical processing of metals, and microstructure property correlation. A very warm welcome, Dr. Patra, and thank you so much for joining us today.
Thank you. Thank you for the nice introduction and opportunity.
Our pleasure. Our next panel speaker is Mr. Sankadeep Mandal, DGM, Product Development Group, Metallurgist, Jindal Steel and Power. Mr. Mandal commenced his professional journey at SS Steel Limited. Over the course of his career, he has accumulated a significant amount of experience in the field of flat hot roll product for a duration of approximately 15 years. His area of expertise predominantly lies in thermomechanical processing, wherein he possesses extensive knowledge and hands-on experience in effective controlling advanced accelerated cooling machines such as MULPIC and ADCO. His proficiency in this domain includes the development of various grades through the implementation of quenching and tempering processes. A warm welcome, Mr. Mandal, and thank you so much for joining us today.
Thank you so much for giving us the opportunity.
We will also be having Dr. David join on the panel along with the other speakers. And the moderator of this session is Mr. Manish Kulkarni, Director, Pro MFG Media. A brief introduction about Mr. Kulkarni. He's an electrical engineer having over 3.5 decades of marketing, business development, and project management experience across manufacturing industry. He has worked at various locations in India and Southeast Asia. An avid reader, Manish also loves traveling and networking. With that, over to you, Manish, for the panel discussion.
Manish, you are on mute. Manish, you are on mute.
Am I audible now?
Yes, yes.
Yes.
Sorry for that. Sorry for that. Thank you so much, Ramya, for the kind introductions of all the panelists. And we are extremely privileged to have these subject matter experts and thought leaders representing academia, industry, and end users. And also Dr. David Crother, the Vanitec UK technical consultant, who has given us a brief overview of vanadium and the applications of vanadium across different industry areas. So, in fact, I was just going through the presentation again of Dr. Crother, and this theme of this technical webinar is vanadium for high strength steel. So I must say that the letter V stands not only for victory, but it stands for vanadium. During this brief the panel discussion, I will be asking questions to each panelist, and I would request them to perhaps use a presentation slide if they want to answer these questions. And we will also take some questions from the audience. So I would urge the audience members, participants, to please post your questions in the Q&A box, not the chat box, but the Q&A box. And we will take up the selected questions from there to and also mention who the question is addressed to, so that we can ask the respective panelists to answer these questions. The whole idea of creating this engagement initiative is to foster collaboration among different stakeholders for vanadium in alloy steel, and to understand what is the roadmap ahead and what are the key opportunities exist in both research as well as in manufacturing and the end use of vanadium in alloy steel. Dr. Crother mentioned about Vanitec's current collaboration happening both at IIT Kharagpur and IIT BHU Varanasi. So let me begin my first question to Dr. Debala Chakrabarti on what specific unexpected areas have you identified in the current understanding of vanadium's role in enhancing material properties? And Debala, could you also provide insights into how your research addresses these areas and contributes to the broader knowledge in this field? Debala, over to you.
Okay, thank you. Thank you, Manish, for the introduction. So let me just share my screen quickly because I want to show you some slides that I drafted. So what we were doing is a project funded by Vanitec Limited. Dr. Dave and his team from Vanitec has funded this work. And we are doing this in collaboration with the Steel Authority of India Limited. So the project is running at Kharagpur, and SAIL is actually our industrial partner. So coming to the work, first of all, we tried to address that what are the competitors of vanadium. We know that niobium is one of the biggest competitor, and titanium. So these are the called microalloying elements in steel, because at very small level, this niobium, titanium, and vanadium can enhance the steel properties. And properties means strength, ductility, toughness, and other requirements. So how these do that, these elements, first of all form precipitates. So there is something called precipitation strengthening. And the next thing is called grain refinement, because there is something called grain size. And if the grain size can be restricted to a very fine size, then the strength, not only the strength goes up, but also the toughness of the steel improves. So toughness is a property that resists the steel to failure, particularly from catastrophic failure as we can encounter in thick steel products like sections or bridge during very adverse situation like a very low temperature, earthquake conditions and things like that. So if we look into the niobium as an alloying element, it's certainly very popular as a microalloying element, but there are some disadvantages also. And one of the technical disadvantage is it can cause a grain size variation, because what we want is not only a very fine grain size, but very uniform grain size, that all the grains we want to be fine. But niobium has some issues that can create grain size variation, and particularly the coarse grains can affect the impact toughness property, which is very much requirement in modern steels, because besides strength, our toughness requirements are also becoming more stringent. Second, there is something called rolling load, because the steel has to be rolled in an industry and the mill has to be capable to roll the steel to the particular size. So the rolling of these niobium kind of steels are more complex, because not only it requires higher rolling load, but also it requires some very controlled rolling facility. That means you have to roll and then you have to hold for some time and roll again. So that can hamper the productivity as well. So this is the second point. And often to restrict the grains to the fine size, these niobium steels require side control rolling, accelerated cooling treatment. Installation and control of such an unit is quite expensive. So in these areas, vanadium can be very useful because it can be rolled at a relatively high temperature without the need for any control rolling. The rolling load requirement remains much lower. And then if we can control the cooling path, then we can get a very fine precipitation. Vanadium precipitation is much more fine and much more uniform, and we get a very fine grain structure. So this is the nutshell, in a nutshell, this is the benefit of vanadium. So let me just quickly show you a few images. This is what is called grain size variation. You can see very, very coarse grain in between very fine grains. So these coarse grains, when associated with coarse precipitates, they can be seriously detrimental to the toughness. So this kind of microstructure often arises in niobium microalloy steel, which we want to avoid. And as I said, we need a very fine and uniform grain size distribution. So what we have done in our study, let me quickly go through that. We had some of the steels where we added niobium, titanium, and vanadium, all these elements, against some of the steels we have melted only with vanadium with varying nitrogen and carbon content, just to compare that how the niobium steels or titanium steels perform in comparison to vanadium steels. So ASCA structure were quite similar for all those steels. But what happens is, as I said, that these elements like niobium and titanium goes through segregation. Segregation means clustering of alloying elements at certain specific location. Like when we do some cooking, if we add spice, we want spice to be uniformly distributed in the soup. But if in some place this remains clustered, then that is really a horrible situation. So that is what is called segregation. And niobium and titanium can segregate up to 5 to 8 times than the nominal composition. So if I am adding 0.05 niobium in the certain region called interdendritic region, its amount can be 8 times or 7 times more than the average. And that is the biggest problem. Whereas vanadium is much less prone to segregation, and it segregates maximum 1.8 times, which is only in ideal condition. In actual condition, it is even below. So this is what the niobium segregation looks like. So in the ASCA structure, if you see the dendritic structure, and niobium is seriously segregating. And in some region, like interdict region, the concentration of niobium is much higher because it's prone to segregation. And as a result, we see non-uniform precipitate distribution. Where niobium is more, their niobium precipitate is more. So you see all these white dots are precipitates, and in the middle of this image, large number of precipitates, but in the surrounding region, it's almost very low precipitate density. So this is what is the outcome of segregation. It creates a non-uniform precipitate distribution. And because of segregation, the precipitate size can be many times higher than what is expected considering nominal composition. Because if certain region niobium is segregating, naturally the precipitates that will form will grow into large size, and those precipitates can even reach several micrometer size and form something called eutectic compounds at some locations. And if this kind of hard particles are present, then this can be really detrimental to the properties like toughness, as they help in crack initiation. And these precipitates control the austenite grain size, because before rolling, we have to reheat the steel to austenite domain at 1200 or 1150. And at that temperature, these precipitates actually pin the grain boundaries. And here, this is the evidence of scanning electron micrographs showing the precipitates, white dots, pinning the austenite grain boundaries. As a result, what happens? At low temperature soaking, which we generally do not prefer in our rolling mill or section mill, there, low temperature, you may find more uniform austenite grain structure, but at high temperature, that can be highly non-uniform grain structure. And these non-uniform grain structure can, after rolling, can result in this kind of grain size variation, which is one of the biggest problems for niobium steel. And it creates grain size bimodality. You can see in certain cases like this red colored grain size distribution plot, y-axis is frequency, x-axis is grain size. It's showing a bimodality, because it means there are fine grains along with that coarse grains. And as I said, this coarse grain can be very detrimental to the properties. What is happening is, in some region, a lot of precipitates pinning the grains into smaller size, and in other region, very less amount of element is present, so their grains can grow freely. So this is a big problem in niobium microalloy steel. In titanium, also, this is a huge problem, because titanium forms a very stable titanium nitride precipitate. And if there is segregation, naturally those precipitates can become many in number and large in size. So in this image, you can see so many titanium nitride precipitates, cuboidal shaped, hard and brittle particles. So those can initiate cracks very easily. So what can happen is, if we add titanium a little higher level, 0 to 8%, more than 0 to 8%, typically titanium segregates, form very coarse titanium nitride. These titanium nitride particle acts as the crack initiators. You can see this image, that how the particle is initiating the cracks, either by cracking themselves or by separation of the interface, and the impact toughness can become much higher. If we remember, Titanic sank where the water temperature was -2 degrees centigrade, because the steel has a ductile brittle transition temperature of +30 degrees centigrade. Now the steel requirement is we need the DBDT less than -60 degree or even lower, so that even in the very cold terrains, the structure remains very safe. But if this kind of things happen, then it's a worry for us. Vanadium steel is much better in this respect. You can see it can have coarse grain size, but uniform grain size. This is the austenite grain size that's happening at high temperature. Depending on reheating temperature, grain size can vary. But the good thing is, grain size variation does not appear. Here, the grains are uniform in size. And then after rolling, you will find grain size will become very fine and uniform, and precipitates remain very uniformly distributed. This is how the precipitates, very fine precipitates. These are the vanadium carbonitride interface precipitates that we have found in our steels. You can see this is called interface precipitation, uniform precipitation. All the grains you will find it's same because of the lack of segregation of vanadium, which is the advantage. And it gives very good strengthening. Even if there is a vanadium nitride formation, its size remains much smaller, in the nanometer level only. So these are not at all so harmful that as titanium precipitates. So by this, we have done extensive work and prepared several melts and achieved, see, the vanadium microalloy steel grain structure. If you remember the earlier one I showed, and if you see this, the grain size is much more fine and uniform. And properties, if you see, we are meeting in sections and plates that we are rolling, we are achieving properties of 450 MPa YS requirement, as we call it E450, or even higher E500 grades we are achieving. You see the kind of strength we are achieving, yield strength 410, 50 MPa and with necessary impact toughness. So overall, this is what I want to show. And as I said, the biggest advantage is this vanadium steel. One of the biggest advantage it remains is rolling load remains low. So the steel becomes rollable. Cracking problems do not appear since we do not need low temperature deformation. And here I have some complex equations to justify why the rolling load remain low. And as I said, that it does not require control rolling facilities, it does not require accelerated cooling facility. So it's a much win-win situation, I would say, from this perspective. Of course, niobium has its own advantage in grain refinement, but this grain size variation is not a desirable phenomena, where vanadium is much better in this respect. So overall, this is my answer. I hope I can.
Yes, Dr. Chakrabarti, it was very comprehensive, and you explained very well the grain structure and the comparison between niobium, vanadium, and titanium. And also you mentioned about the rollability and the advantage of using vanadium steel. So it is very interesting. Of course, we have representative from the other side of the industry, and we will also pick up their brain about these aspects. From IIT Kharagpur, let me move to IIT BHU Varanasi, and we have Dr. Sudipta Patra from there. And I would request Dr. Patra to give his views and understanding of vanadium's role in the material property enhancement and this aspect, Sudipta.
Yes, thank you, Manishji. So I have shared my screen.
Yes.
So uh, we are doing this project for last 1.5 year, say. So we are trying to develop high strength, high toughness vanadium microalloy steel for a heavy gauge plate, especially greater than 50 thickness plate with Jindal Steel and Power, our partner, industrial partner. So basically, the problem of these grades are in high thickness. Difficult. It is very difficult to achieve the mechanical property like greater than 50 thickness. So normally these steels are preferred in normalized condition, because in normalized condition toughness is also very high, and the requirement of strength and toughness is given here. You can see minus 50 degree 27 joule impact toughness is required, and 460 MPa YS is required. So this is the chemistry standard as per the EN 10028. So you see there is a scope of vanadium addition of 0.2%, and there are other alloying element also. But we will try to develop this steel with vanadium and nitrogen. So here the literature review and scope is that there are many literature on these vanadium alloyed steel and its precipitation strengthening, but the unique is in the normalized condition when we are trying to austenize at 900 degrees centigrade temperature. There you know that some precipitate will dissolve and some precipitate will undissolve. So these we always want the undissolved precipitate. We always want the dissolved precipitate, so the vanadium will be in the solid solution, and then when we cool it, we will get the fresh precipitate and very fine precipitate, so that we will get the very high precipitate strengthening. But at the same time, if we have the undissolved precipitate, that will pin down the austenite grain boundary, and they will not allow the austenite to grow. So we will get very fine grain. So there is a competitive effect of grain refinement from the fine austenite, which will come from the undissolved vanadium nitride precipitate, and also the precipitate refinement from the dissolved and fresh reprecipitation. So that is one aspect which we thought is very interesting. And then the another aspect is vanadium and nitrogen optimization, particularly in this case. So then another thing is that when we are having this rolled hot rolled plate, so there are other strengthening mechanisms such as maybe some dislocation strengthening also, and together with dislocation strengthening, grain refinement and precipitate strengthening. But in case of normalized plate, we have mainly the grain refinement, grain boundary strengthening, as well as the precipitation strengthening, uh, little low dislocation strengthening. So we are also exploring the effect of higher carbon and manganese up to say 0.2%, which is allowed in the standard. So these are the aspect we are studying. So we have melted almost 4 varieties of steel out of these initial decided chemistries. And then what we observed that if we add nitrogen, then my precipitation dissolution temperature is also increases. So many precipitates are undissolved at the temperature of my soaking at 900 degrees centigrade opposite said. So there we will get very good grain refinement. So then we also have observed that if we add some aluminium for deoxidation, say if we allow 0304 aluminium, that is will also that will also actually compete with vanadium for the nitrogen and their precipitation with of aluminum nitride. So there we can also lose the strength. So we have to keep this aluminum in lower chemical composition. So then we have measured the temperature profile, and then we have taken these 4 chemistry, and we have melted in a vacuum induction furnace, and then we rolled, and we have got this type of ferrite pearlite microstructure. Now with this chemistry of 0.15 vanadium and 90 nitrogen, we could achieve 520 YS and 702 UTS and elongation in the as forged condition. But when we annealed it, a little bit less in strength, but we could get very good impact toughness. Here you can see with high vanadium and high nitrogen, we could get even 70 joule impact toughness and minus 50 degrees centigrade temperature. Here we are not adding any alloying element, only vanadium and nitrogen and little bit amount of carbon manganese steel. So the EPSD analysis also shows that high angle grain boundaries of high percentage showing the recrystallized structure. And then we have varied the temperature of oxidation also, and we have observed that as we are increasing the oxidation temperature, our precipitation, due to the precipitation strengthening, our OIS also improves. First it is decreasing and then it is increasing due to the high precipitation strengthening when the precipitates are dissolved state and then reprecipitated. So therefore again we have taken this 150 nitrogen steel at higher temperature. We can see that the vanadium precipitates did not dissolve here, and as the precipitation stability it is high in case of 150 nitrogen. So so in this case we have observed that the high nitrogen content can lead to the very good grain refining, and the grain will not grow because of the precipitation stability here in case of high nitrogen and high vanadium steel. So the precipitation strengthening effect will show the good hardness also here with the normalizing temperature. And we can see the micro hardness in the ferrite region. You can see that in the as forged condition we could see 200 Vickers hardness in the ferrite itself, and in 990 degrees centigrade we could again get 185 hardness. So here we have also tried the combination of niobium and vanadium. Here also we could observe very good grain refinement and as well as the precipitation strengthening effect. And here also we could get 460 around 460 470 MPa yield strength with good elongation and UTS. So in this with these 4 alloys we could calculate the precipitation strengthening, and we can see that 246 MPa precipitation strengthening itself can reach this value with high nitrogen and a little bit lower nitrogen, 90 nitrogen and 150 nitrogen we could get. In the exposed condition we could get these values, and also at higher normalizing temperature also we could get very high precipitation strengthening values. So you can observe the precipitation strengthening as well as the high strength and high precipitation strengthening. So the TEM observation of the precipitates are presented here. We could see very fine precipitate 2 to 17 nanometer is the precipitation range. Because in this condition, some of the vanadium nitride precipitates are high, coarser in size, but very fine precipitate 2 nanometer size precipitate also can be observed in the bright field and dark field images. And some clusterings of precipitates are also there, but there are very fine and uniform precipitate, mainly maximum size is 80 nanometer. So as Professor Devala Chakravarti also mentioned that vanadium nitride, though it forms at high temperature, the vanadium precipitates are not very coarse. Vanadium nitride precipitates is here in our case around highest is 18 nanometer, and very fine precipitate 1, 2 nanometer, 10 nanometer precipitate we could observe here. So these are the STM head-up map. You can see the vanadium distribution, very fine vanadium distribution here. And in here, the unique point of 150 nitrogen is that at 900 degrees centigrade also you could see very fine precipitate. They are stable at that temperature. They are present at that temperature to refine the grains. Okay, so with this we can conclude that these vanadium and nitrogen can effectively increase the precipitation strengthening to very high level in both as forced condition and as rolled condition, as well as normalized condition. And this is my answer of the question. Thank you.
Thank you so much, Dr. Patra. Thank you for that very insightful presentation. I will now move to Dr. Sankaran, who has joined us from IIT Madras. And the question to you, Dr. Hello.
Oh, yes, please.
Yeah, Dr. Sankaran is complex alloys often require innovative characterization techniques. Could you elaborate, Dr. Sankaran, on the experimental methods and analytical tools you have employed to investigate the interaction between vanadium and other alloying elements in various length scales? How do these insights aid you in predicting and optimizing the behavior of vanadium containing material under different conditions? Over to you, Dr. Sankaran.
Yeah, thank you, Dr. Manish. I have not prepared any slides, but I was told that it's a panel discussion. So, okay, see, working with this vanadium microalloy steel, for me, it is more than 20 years now. And I started working with vanadium microalloy steel for producing multi-phase microstructures during my PhD days. That is 38 mm SiVS5, that grade, which these days Kalyani Group is producing it. And there the challenge was since the microstructure is a multi-phase, characterizing these precipitates into each individual phase is a huge challenge. As two of my panel members already showed a lot of microstructures, these vanadium precipitates as vanadium carbides as well as nitrides or carbonitrides, depending upon the chemical composition as well as the cooling process. Right? So characterizing them in a particular phase is a huge challenge. So most of the time I'm looking into transmission electron microscopy, especially diffraction techniques. That is what I employed in those days. There also is the challenge is we are not able to, I mean, those days, I'm not talking about today. Today we have much more sophisticated techniques available. But those days it is very difficult because to identify whether it is carbonitride or carbide, it is again a big question. And again, that is because you see that the lattice parameters of vanadium nitride and vanadium carbide are very close, 0.4118, 4152. So in diffraction also, it is very difficult to distinguish if we would get in a composite diffraction pattern. So this used to be my key challenge. So later I worked on this microloid steels meant for high beams, structural beams, or any bridges. This was work done in my postdoc. There, people used not just vanadium in combination with vanadium, niobium, and vanadium, niobium, titanium. And like that, several grades, they used multiple alloy, microalloy elements. So that creates much more complex intermetallic precipitates, not just carbides, nitrides. It is vanadium, niobium, titanium equally, they take part into this precipitation. So you have duplex precipitates, triplex precipitates, and it used to be a huge challenge to characterize them, which one is what. Because, okay, at the end, we know that the outcome is refined microstructures and improvement in the strength and toughness and so on. But academically, if you want to look into this aspects, what is the crystal structure and what kind of complex crystal structure it forms and how it affects the properties, that requires little more deeper analysis. So what I used to do is I used to do the carbon extraction replica techniques. So I used to do this carbon extraction replica and then take this individual precipitates which forms in different morphologies, cuboidal, spherical, irregular, needle, all type of morphologies. It evolves depending upon the cooling rate and the process and so on, because these samples we used to get it from the industries those days. Am I audible?
Yes, sir, you are very much audible. Yes, please go ahead.
Okay. Suddenly something has happened to the screen, so I thought I'll check with you.
No, actually, there was some error in terms of sharing of screen, so it was not unshared. So it is okay now. Yeah.
Okay. So what I used to do is I used to take all this precipitate extracted on the carbon extracted films, and then do individual EDS, and then take the spectral ratios to find out the stoichiometry. I mean, it is a qualitative stoichiometry, but then it gives an idea what kind of intermetallic it forms when you use more than one microalloy. People use for different purposes, but then and characterizing them is a huge challenge. Like as I said, some of the precipitates are quite intriguing because it forms a core shell kind of a precipitate, a core being a nitride and the shell being a carbide. So this is what my research finding found out. All of them are published a long time back. I can give you in the reference if anybody is interested. So that was about that postdoctoral research and so on. And later, when I came to Madras, and then again we used these vanadium and niobium microalloy steels to produce ultra fine grain steels. Okay, so there again we found a challenge because characterizing this complex precipitates remained a huge challenge, because again the microstructure is so complex, because we wanted to produce very ultra fine grains, but the grains were completely filled with it's a dual phase microstructure we wanted to produce. So you have martensitic and some bainitic phases are very complex, and to identify these precipitates forming in these matrices is creates a lot more challenges to characterize them. So again, we tried these kind of replication techniques and then characterize them. There again, we found that these precipitates, they just not very straightforward to characterize, because it forms a complex. Like if you are using a simple vanadium alone, there again we can assume that at least it is vanadium carbonitride. There also you have to see what is the nitrogen content and what is the vanadium content and so on, we can come to some conclusion, because the electron diffraction techniques, which gives a very nice diffraction pattern, which, because the vanadium carbide is in a L12 ordered structure, so you will get such a nice pattern. But then the vanadium nitride also will have the similar lattice parameter, which also will fall into the same kind of structure. So again, it's a challenge. But if you add niobium into it, then again the complexity goes more. It forms a coastal structures, and depending upon the cooling rates. Of course, since we were interested in ultra fine grain and so on, and high strength material are improving the toughness, then based upon the cooling rate, the ferrite morphology also changes to polygonal to last type of ferrite and so on. Again, the complexity increases to characterize these microstructures and so on. So yeah, these are my challenges, but I still rely on electron diffraction to characterize this. But today we have luxury of using atom probe tomography technique. But I have not used it yet. But yes, this is my first reaction.
Thank you. Thank you, Dr. Sankaran. Thank you so much. And I would, of course, we have the expert from the steel industry as well as the end-use industry from the passenger automotive vehicle. Before moving to them, let me also tell the audience that while during the registration process, we have received several questions, and we will take them up as we go along after I finish some of the questions which I have prepared. And also, I will take a pause here and ask Dr. David Crother to have if he has any observations on the proceeding so far, and does he have any comment to make on Dr. Sankaran and Dr. Patra and Dr. Debale Chakrabarti's presentation?
Thank you very much. Yeah. Well, I'm very interested to hear the presentations of all the panelists so far, and I think it shows the depth and the knowledge of vanadium-containing steels that are shown in some of the Indian research centres. And I'm also very pleased to see the relationships between the academic people and also the steel companies, because academic research is great, but really we want to see those academic results translated into an industrial process, an industrial product, so that we can see a benefit to the wider society of the research we're doing. And I think we can see that in all the replies we've seen so far, that academic research, looking at the details of vanadium precipitates, the details of grain size distribution, it's not just an academic thing. It translates into real world products with improved properties, which make the world better for everyone. So I'm glad to see both the knowledge and the interaction with industry and real world products. So very interesting to see.
Thank you, Dr. Crother. Thank you so much. And the precise idea behind such engagement initiatives is to bring the academia, industry, and researchers together to understand the trends and how it can be made better to solve the industry problems and challenges. We have Sankadeep Mandal from Jindal Steel and Power, and I would request him, in the value chain, we go from academia to the steel producer, and then we have the end user. Senthil Kumaran is with us from Mahindra. But Sankadeep, my first question to you is, could you elaborate on the nuanced influence of vanadium incorporation on the integrated mechanical attributes of diverse steel products? Additionally, can you please highlight specific domains where the integration of vanadium proves particularly advantageous? Sankadeep?
Right. Yeah. Thank you very much for the questions. Yeah, understood. So, the part of the vanadium additions, because the vanadium addition in the high strength steels are, since we're using for the long time, that we're doing for the normal general applications for the structural segments, the strength level, when it is moving away from the 350 megapascal towards the above, like close to 550 megapascal or 700 megapascals, then vanadium additions is obvious in the steel, that been falling for since long. Yes, the vanadium additions, along with the nitrogen level to maintain in the industrial level to control the vanadium nitride or carbonate precipitations is always a challenge, because there are lot many equilibrium conditions, and as well as the non-equilibrium conditions will be imposed in the during the thermomechanical processing as well, during the process of the entire rolling operations as well as the cooling operations. So it's always a challenge in the industrial sphere that to maintain the properties to avail this precipitation strengthening benefit, and definitely the precipitation strengthening and as well as the grain size control will be also an important factor for the grades that right now we are producing. So in my aspect, the strengthening mechanism and the grain size are basically contributing to the strength of the steel. If you look into the any high strength products, the 70% contributions is coming from the grain size and the precipitation strengthening. So the total contribution towards the making any high strength steels, where always the steel manufacturer always uses the strengthening mechanism as well as the grain size. Grain size mechanism controlling, there are several processes that are adopted, across the processes. There are processing techniques like recrystallized control rolling, the thermomechanical processing through controlled deformation techniques, the different temperature regime. There are different temperature control mechanisms are there in the new generation mills, where we can precisely control those deformation temperatures, where the strain induced precipitations can contribute to the strengthening in the field of if in the case of vanadium or in case of niobium. But if you look into the vanadium, yes, definitely Dr. Devalai Chakrabarti has rightly said about the microstructural uniformity will be better in the vanadium nitride or carbonated precipitates, because the rolling industry, when we are going for the vanadium bearing steels, then we can do that the high temperature kinetic, maintaining the high temperature rolling, and it is close to the recrystallization temperature. So if I'm going to do that temperatures, the thing is that the vanadium is going to precipitate just after the finishing on the rolling part, and then it will be contributed and it will get enough time to precipitate on the interface during the phase transformations, and giving us the very homogenized structures that benefit both the ways, strengthening as well as the improvement in the CV and toughness properties. So that is the very important things to control, where the other alloying like niobium and others, where probably those facilities will not be there. There has to be a strain induced precipitations as well as the lower temperature deformations needed to get the maximum benefit of this strengthening mechanism to achieve in these steel products. In terms of producing the different applications aspect, so the vanadium we're using mostly beyond the strength level of 350 megapascal in most of the cases, which is almost close to the 20 to 30% cases, the entire production, that is happening. And the new segment is coming off. This is the normalized segment of the high strength qualities, where the strengths are coming. The demand at the strength level is beyond 450 megapascal or the starting of it, but the material has to be supplied through a heat treatment process through a normalized, not in the quenching tempering. So the challenge is that whenever we're doing the normalizing operations, so there'll be a the softening in the entire matrix, the palette matrix. So definitely there'll be obvious lowering the strength at the final, both the strength and the UTS. Definitely the impact properties and other properties will improve because of the grain refinement. There is another thing apart from that also, but we are also losing the strength because of the softening of the entire matrix. So how to get the benefit of the precipitation strengthening to get to retaining those strength even after the heat treatment operations, and normalizing or annealing treatment is the challenge. And the challenge will become more, severe when the plate or any thickness of the hot roll products will be higher. Because if I'm going to roll a 40 millimeter plate thickness, then there'll be not much struggle, because the conventional mills and the new generations mill having enough strain-induced straining capacities through thickness that it can homogenize through a deformation process. But when going above beyond 80 millimeter or 100 millimeter or 150 millimeter plates to be produced through such strengthening mechanism, then there is a obvious contributions there for the vanadium aspects, because we have seen industrial practices that the addition of vanadium will give rise of refinement as well as the refined level of at least 15 to 20% in the refinement in the entire ferrite grain size, and as well as the strengthening also will increase significantly for the thicker sections. The homogeneity I'm talking about for the cross section of the thickness, because it changes when you have the higher sections, the entire microstructures in the cross section will get changed. The strength will get changed also in the across the profile of the plates or whatever the hot roll products. So that part is very important to understand the industrial challenges. And then obviously the vanadium is contributing much for thicker plates, producing thicker high tensile products. And there is a demand in the Indian market also for the high tensile thicker plates production. And definitely there is a additions of vanadium will be much more play a pivotal role on those segment where we're having the high strength thicker plates producing with the superior CV and toughness properties. So that is there. And yes, I want to just convey another one thing, that vanadium is having having a very good characteristics controlling the corrosion resistance properties, in terms of there are probably not much research is being done on those aspects. But if you see industrially, the API line pipe segment, the SAO service segment is having a lot more markets where the material has to sustain some requirements like the corrosion testing, where the the S2S components are creating the hydrogen embrittlement in the steel. So there are specific microstructural techniques to control those hydrogen embrittlement in these structures. And vanadium is creating a very big role on those aspects to control the hydrogen flaking or the hydrogen embrittlement in these structures. We have certain industrial practices that we have followed, and we have seen that the addition of vanadium is giving us the lot of benefits of resisting the hydrogen cracking through the SAWA service testing, like hydrogen induced cracking testing, or SAWA service testing, the sulfide stress corrosion cracking testing. So this is having a significant roles playing with the other alloying, like if I'm going to combine with the different alloying techniques like the chromium along with chromium copper with vanadium, so it is having a different dynamics of controlling the corrosion resistance properties in the steel structures. So that is all that is from my side, Manish.
Yeah, thank you, Sankadeep. One
you.
out of syllabus question to you. You are pursuing your PhD from NIT Rourkela. What is the subject?
This is for the thermomechanical simulations. Actually, for the thermomechanical simulations for the hot products only.
Best wishes to you.
So we have probably doing my PhD, so we have probably a comprehensive models that can predict the entire the properties at the final level of including microstructures, including the final properties, including CV and toughness properties. So considering all aspects of deformation, dislocations, precipitation, strengthening, so combined together to give a model that can predict any kind of steel properties, the final.
Very interesting. All the best to you. And let me move to the passenger vehicle industry represented by Senthil Kumaran from Mahindra & Mahindra. Senthil Kumaran, the collaboration between metallurgists and automotive engineers is quite pivotal. From your perspective, how do you see the future trajectory of incorporating vanadium-rich steels evolving in passenger vehicle manufacturing? And are there any specific trends or innovations on the horizon that could further amplify the role of these materials in enhancing vehicle safety, efficiency, and very importantly, sustainability?
Yeah, I think,
Senthil.
Thank you. First of all, thank you for having me here, Manishi, and the entire Vanitec group, Dr. David. And it was very happy to, sit amongst the professors and, getting into the grind of physical metallurgy once again. I think that was really heartening. So I think you have, see, of course, from the end user perspective, I think we don't any longer we are metallurgists, we are material scientists or materials engineers for automotive industry. Fortunately, we are part and parcel of the design fraternity, right? So that is the reason what in a lighter vein we say that we romance many materials, or we romance all the materials. I think it's more like horses for races for them, for us actually. Coming to the three musketeers, if I may call, the niobium, titanium, and vanadium, I think particularly for the flat products, there is a lot of opportunity going forward. There are two areas in the body design. I think you must be aware of the lightweight index, right? The global stiffness of torsional and bending of the BIW is very, very essential for the performance of the vehicle in terms of reliability, durability, NVH performance, as well as the crash behavior, right? So definitely both niobium, titanium, and vanadium, combinations of them is very essential. One of the most important area is the uniformity of the properties. When you talk about the crash behavior, the scatter band analysis is being done. Say, for example, I have a 5-star car, right? Euro NCAP 5-star car, and then I need to have the repeatability of that particular behavior of the vehicle in the crash behavior. So this is what we have pitched in the Bureau of Indian Standards also. Like the band of operation, we need to kind of tighten it. That means gone are those days wherein the designs were done using monotonic properties, only YSTS and percentage elongation. Now we work on Gizmo models, we work on the MAT 24 LS Dyna models, and an array of mathematical models have come in for a whole vehicle crash simulation behavior. So it is not one element or one material. For example, we have a composite, long fiber composite in tandem with, say, DP780, right? Or we have, nowadays we are having high strength aluminum also into this particular thing. So how do we kind of choose the materials accordingly so that you get the optimized behavior? This is one of the important aspects, and everybody are aware. And one more aspect is the whole expansion ratios. Of course, that is one more edge ductility behavior is also very important, particularly for the chassis application where it is fatigue intensive. I think I spoke about the scatter band and how vanadium can play in this particular important area. The other important aspect is I think one of the most important this thing what I can remember is air-cooled forging or control cooling forgings. I think that is now it's a complete spectrum is covered, right from forging front axles or the rear axle, the suspension arms, the Conrad crankshaft, 49 ms or 38 ms VS5. All these particular grades have penetrated, even 1541 with some kind of a micro elements also, some of the steel mills are producing. So the forging side of it, wherever vanadium penetration is, I would say is a very, very advanced stage. So as the dual phase DP grades and HSLA grades are also. But we can see say for example, when we see JSW, they use more vanadium. Okay, there are some other steel mills who prefer niobium. But most important aspect is how the steel mills guarantee the particular property and guarantee the scatter is what is very important. As a materials scientist or a technologist, we generate this particular card for the consumption of the CAE fraternity who decides the geometry of the various vehicle things. So this is one area. Second area is of course spring steels. I think SOUP 12V kind of material or derivatives of that particular material. I think we are using in our pickup vehicles as well as small commercial vehicles. We have parabolic springs coming in. people are migrating from the conventional flats to parabolic kind of a thing. So the reheat behavior and the higher fatigue life is required. See, we need to reduce the number of springs, leaves, right? Instead of 4, we wanted to become, we need to take only 1. So lightweighting is so essential. So I think this is one area. I think vanadium spring steel's penetration has to be much higher. This is our viewpoint. And the other thing is, of course, there is a new interest in some of the sportier vehicles. I think in the near future, people also may look at titanium 6 aluminum 4 vanadium kind of things for coil spring applications or disc spring applications may come up. You may not, it will definitely not a surprise if it comes to the Indian market. Another important area is the automotive tubes. I think, not only the seamless kind of tubes, the ERW tubes also extensively used for the suspension application. And there are a lot of such kind of an ERW tubes in the crash bars, crash beams kind of a thing. How do we, and these particular things are either made by crush forming. Subsequent to ERW, the crush forming happens, hydro forming happens on them. And nowadays, there is a trend on air forming also, hot air forming. That is a substitute to the hot stamping, right? So this is a new technology, and people like Sumitomo are getting doing a lot of research in this particular area. Automotive industry also looking at these kind of technologies for doing the lightweighting. I think this is a lot of areas that is still to be tapped. And one more area I think rightly is mentioned about the corrosion resistant behavior. If you really look at the electric vehicles, there is the torque is increasing, and the torque generated is instantaneous compared to the conventional internal combustion engine. So I think more and more regenerative brakings are also coming in. So that means, the chances of the actual braking happening is reduced to a larger extent. So you'll have rust particles coming onto the thing that will create a lot of NVH issues when the stoppage happens, brake application. And one more thing is, since the NVH behavior has to be improved, you go for higher carbon equivalent cast irons, and that have a problem with respect to the strength and the hardness. So I think vanadium can be really looked at it this kind of a new avenues for electric vehicle brake disc and drum kind of an application. I think more work can be looked at it. I'm really heartening to see in the flat products. I think there are scope available for activities in the area of castings as well. So this is one thing that I just wanted to kind of touch upon. And the other thing is I think Mahindra, we have, for example, 2040, we have a carbon neutrality target, and we are part of the Green Steel Consortium, wherein we have kind of, given a internal target of 10% green steel usage by 2030. See, today we are at something like our group consumption is 7.8 lakh tons of steel we consume, and it is bound to go to 12.8 lakh tons of steel by 2030. So if you really look at it, 124 metric ton of green steel we have already promised to consume. And I think we cannot go and tap only people like SSAB or some people who are having the direct kind of a reduction. But those kind of things may reduce from the current 2.6 ton of CO2 per ton of steel produced, like a carbon footprint, to the level of green steel, which is less than 0.4 ton of CO2 per ton of the same. But what is more important is how do we kind of do more of scrap steel? Using scrap steel, how can we produce automotive quality, okay, with all the formability, weldability kind of things? So that is one area of research that would be really useful And I think there would be a government support also in terms of circularity. In fact, Ministry of Environment and Forest and CPCB, there is a draft that is released recently, and then they have really given targets on circularity. Particularly, even they are demanding 20% of scrap steel to be used in a new car produced from 2026. It goes up to 30-40%, as the year progresses from 2030 to 2040. So I think there is a big push from the government of India also on this particular thing. And we also have a lot of ESG and commitments. There are a lot of investors who have invested in green technology like born electric vehicles. In fact, there is a push from these financial institutions and investors also, wherein we need to work more on this green steel technologies, green steel and steels from recycled thing. How vanadium can play a pivotal role in kind of enhancing this particular property, narrowing down the band. That would be a real kind of a contribution and penetration from the vanadium side of it. I think these are all the few points that immediately come to my mind, Mr. Manish.
Senthil Kumaran, I must thank you for this comprehensive answer. And in fact, you are you are an example of marriage between metallurgy and metallurgy and automotive engineering, because you did your metallurgy and materials engineering, and then you did your masters at IIT Madras in automotive technology. So you are a perfect example of this collaborative thing between two different streams. There is one audience question which is related to your segment, so I will ask a quick response from you. What is the role of vanadium in high-strength cold-rolled annealed steel for automotive segment? Please shed some light on this subject.
Yeah, so if you really look at it, I think I told about the stiffness-based designs and strength-based designs, right? So strength-based is like the energy absorption members, particularly nowadays we are using, the floor has become flatter, right? You have electric vehicle, you have a flat battery, you don't have a transmission tunnel exactly. So we are moving to say higher grades like DP 590 and upwards. So that is one trend. And second thing is all the reinforcement areas. There are areas like seat cross members, right? This also, and then sill reinforcements. These are all the areas which are predominantly deploying DP 780 and DP 980 kind of materials. And this is where the vanadium is really playing a pivotal role. So I can say in terms of improving the properties and guaranteeing the properties this is having. And then we are also now comparing the MAT24 cards for the same steel grade with the different strengthening mechanisms. What, one side is on the niobium and on one side is on the vanadium kind of a thing. I think more and more such kind of a research beyond the monotonic properties we are looking at it. And I would say this is one spectrum of steels for crash performance where vanadium is kind of getting prominent. And of course, for the spring flats, we are really looking at vanadium. And control cool forgings, yes, they are kind of there already.
Absolutely, yeah. So you touched upon the sustainability, safety, these aspects which are so crucial for the segment, for the automotive sector. I will request my colleague Ramya to run a poll question so that the audience can also participate in this, and we will know their views on this question. So may I request Ramya to please run a poll question? Yeah, it's there on the screen. What is the most promising area of research for the application of vanadium containing steels? And the options are there on the screen. We'll close the poll in another 15 seconds and then also display the results for everyone to see. as Ramya had announced earlier during her opening remarks, there will be a lucky draw. So please stay back till the end. The lucky ones will get some exciting prizes. If you have received responses, then you can close the poll and display the results also. Yes, so it's quite equally divided, right? Very interesting. Very nice. We'll take a screenshot of this so that we have the results with us. And now there is also there are some questions which I said that we received during registration process, and some of them were answered during the deliberations what we had so far. Before I move to one question which is there in the Q&A box to Debale and Sudipta, I will request David to have his observations and comments about what we heard so far from the steel manufacturer as well as the passenger vehicle manufacturer.
Thank you very much, Manish. I'd like to make a few comments and try to draw some different segments together. We've heard on the use of vanadium-containing steels in the automotive sector, and we also touched on the topic of hydrogen embrittlement, in particular related to line pipe. But there is a sort of common ground here. Some automotive steels are produced using a hot forming process, in that a flat strip is heated to around 900, and during the forming process, it's quenched to martensite, a very high strength material. And these types of component are used for things like impact resistance, the B pillars in cars, because they're so strong. One problem you see as you go to higher and higher strengths is that these steels are becoming more susceptible to hydrogen embrittlement. And vanadium has a role to play in reducing hydrogen embrittlement. We heard a little about that from the line pipe segment, but it also applies to a lot of other products, including the auto sector. And we've done some work which shows that vanadium precipitates, the vanadium carbides, the vanadium nitrides can trap the hydrogen. The hydrogen interacts with the precipitates. And when that happens, the hydrogen embrittlement effect is reduced. So for the automotive sector, there are several steel types that can benefit from the use of vanadium to reduce this hydrogen embrittlement. Another project we're working on, again related to the auto sector, is the spot welding of these steels, because it's fine looking at the basic properties, but often these steels are welded together. And that welding process can make the steels more susceptible to hydrogen embrittlement. So we are doing a project in collaboration with some Swedish researchers, which is looking on the hydrogen embrittlement of the spot weld of very high strength automotive steels. And again, we see that the presence of vanadium precipitates can act to reduce the hydrogen embrittlement. The precipitates act as trapping sites for hydrogen. So as well as producing high strength steels, vanadium makes these steels more useful because they can act to reduce hydrogen embrittlement. So those are my comments so far. Thank you.
Thank you. Thank you so much. Debale, there are a couple of questions. One is specifically addressed to you and one to you and Sudipta. Debale, how much transformation temperature can be lowered when compared to niobium and vanadium?
Okay, so in vanadium, actually, nitrogen is very important. If we can have nitrogen, actually what it does, it actually increases the equilibrium transformation temperature. And therefore, if we go for a relatively fast cooling also, very fine precipitates can form. And those precipitates are very stable. Compared to vanadium carbide, vanadium carbonitride precipitates are more stable. So you may find a lot of research using nitrovan and things like that for vanadium steels, because it increases, nitrogen increases the driving force for vanadium precipitation. So it is very important in vanadium steels, when we cool, this cooling rate should also be optimum beside nitrogen addition, because Sometimes if we cool too fast, then precipitates will not form. If we cool too slow, then precipitates will become coarser. So to get an optimum precipitate size, I would say whether you choose coiling temperature or cooling rate, if it is a continuous cooling, then it has to be intermediate. Typically, in research, you will find it's people say 2 degrees centigrade per second or something. Some values, if you read papers, you will get. Similarly, for coiling temperature, it's the same. It's an intermediate coiling around 500 is beneficial. Otherwise, if it is too low, then precipitates may not form completely, which may not be useful. So I think in vanadium steels, this cooling and coiling are important. So to some extent, if those are controlled, then it is good. Niobium nowadays, as I said, to maintain the fine grain size, it is recommended even for line pipe steels to go for accelerated cooling. Because people are going for very fine grain or acicular ferrite microstructure. But this control of the accelerated cooling has to be very important because by chance, if phases like benite, upper benite, and these forms, then again, those are bad for the properties. So overall, it may be a bit technical answer, but I hope the message has gone across.
Thank you, Debale. There is a follow-up question, another question on the stainless steel using vanadium. The questioner is asking, we're in the field of stainless steel using vanadium to an extent of 0.05% along with niobium and titanium. The question is, before rolling slab needs to be grinded or not, and if yes, how much thickness needs to be grinded? This question is to both Debala and Sudipta.
Dr. Patra is better to answer.
Sudipta.
Yeah. Actually, Manishji, the question is that if we use vanadium, normally niobium, titanium, vanadium is added as a stabilizing element in the stainless steel. So if you add titanium, so titanium oxide and titanium nitride forms at very high temperature, and titanium oxides are stable, very stable oxides. And during steel making operation, so these oxides they come into the surface of the slabs, and then if we do not grind, at least I think 2-3% grinding is needed overall. I am talking about the overall lead. 2-3% is waste almost, and they grind it from say 200 mm to 196 mm. So then what happens, we are basically losing the material. But that is the advantage in vanadium. If we add vanadium, then this vanadium nitride will not form at that very high temperature. At titanium nitride is around say solidifying temperature they form, and also the oxide is not that much stable. So therefore, I feel that this vanadium addition in the stainless steel will not require that much grinding. Probably you can say 0.5% grinding may be also okay, because we have experienced that with vanadium these surface defects do not come in the cell slab. The titanium oxide and titanium nitride, they normally cause the surface defect. So and if you can control the oscillation frequency of mold oscillation and the negative strip time properly, then these oscillation marks, if you can avoid, you can go for even 0% grinding loss also. So that is my answer, that vanadium addition is very helpful in this point for the stabilization. But one disadvantage is that if we need to use at very high temperature, normally say 321 grade, say very high temperature use, 800 degrees, then the vanadium nitrate precipitates are not stable. That is also a disadvantage. So if we are going to use at a lower temperature, then I think it is better to stabilize with vanadium and niobium rather than the titanium for the grinding, minimizing the grinding loss. Yeah.
Okay. Thank you, Sudipta. Dr. Sankaran, do you have anything to add? And Dr. Krotha, also you may after Dr. Sankaran speaks on these topics.
Yes, thank you, Manish. So the one point which I want to add is like these microalloy steels like vanadium or niobium, they are amenable to this, forming various type of microstructures. Like Jabal has said, depending upon the cooling rate, their response to the cooling rate is bit amazing. And you can produce log type of ferrite or acicular ferrite or polyphenol ferrite or combination or by model distribution and so on. And these are the areas we have tested, and then we have also patented some of these ideas to manipulate this and then exploit this interface precipitation, controlled cooling. These are all some great engineering advantage one should look at it to derive the desired properties. So these are some of the things we have already demonstrated in the laboratory scale, and something yeah. So I think these are aspects we should keep in mind even for the ultra fine grain materials. These strategies will work. Yeah. Thank you, Manish.
Okay, Dr. Krota, any points to be added?
Yes, if I could, I'd like to follow up on the question about transformation temperatures and how vanadium and niobium affect transformation temperatures. As we know, transformation temperatures it's a complex subject, and the transformation temperature will depend on the overall composition of the steel. It would also depend on the austenite grain structure, how fine or how coarse the grain structure is, whether it's recrystallized or not recrystallized. But I'd like to talk about transformation during the welding, which is something I don't think we've touched on so far. During the welding process, we're heating the steel to a very high temperature, and that gives us a very coarse grain size, but it also dissolves any precipitates. So any vanadium or niobium precipitates which are present are dissolved by the welding process. That leaves the niobium and the vanadium in solution. And as the weld cools down, niobium in solution has a much bigger effect on transformation temperatures than vanadium. So in a niobium steel with a weld heat affected zone, you can get very hard, brittle microstructures. We're currently doing a project with some Chinese line pipe producers who are using very high niobium steels, and they've encountered problems with the welding of these steels. And what we're trying to do is to partially replace niobium with vanadium, because the high niobium steels are giving such problems by reducing the transformation temperatures and forming brittle microstructures. So the transformation temperature question is very complicated. It depends on, as I say, many factors. And in some situations, as I mentioned, the partial replacement of niobium with vanadium looks to be giving us benefits in terms of weldability. So that's the point I'd like to make on that topic.
Okay, great. Thank you so much. Let me move to back to the steel producer, Sankadeep. Sankadeep, you mentioned about, of course, various things, including the corrosion resistance, stability. How does the incorporation of vanadium into steel matrix influence the crystalline microstructure? And could you elaborate on the mechanism that dictate the interaction between vanadium and other alloying elements during the solidification process?
Yeah, Manish, the solidification process for the vanadium, steels will have the impact, because along with the vanadium, we are adding other alloys also as well. That already we know that about the main thing is the deoxidizer in the steel making processes, where the aluminum is going to be added much, for deoxidation purposes. And, obviously some certain region, when steel, the addition of aluminum is also, the mandatory things. And in certain cases, also titanium is also going to add. So when it is going to solidify from the liquid stage in the continuous caster, then there will be there'll be two situations in the equilibrium scenarios. There'll be the combinations of the different nitrides, because there are affinities with the nitrogen, with the aluminum, as well as the others like titanium is having more affinities also. So it will form the high temperature precipitates. The titanium is more high temperature precipitates, and then aluminum, and then vanadium will come in picture. Niobium will come in pictures, and gradually it will come down when the solidification process will happen in the continuous caster. So the important aspect of any high vanadium steel with the high nitrogen level in the continuous caster, that the caster should have the good dynamic control on the solidification control pattern, like the water flow controls through a level 2 controls, where we can predict the temperatures or all the unbending or the straightening zones where the stresses will be more, to control the hot ductility behavior during the continuous casting. And definitely the precipitation, considering the thermodynamic equilibrium conditions, we can exactly understand where the amount of precipitates are going to come, either is in terms of niobium carbonitrides or the aluminum nitrides or the titanium carbonitrides, or because these are all co-precipitating during the solidification processes. So the combination of alloy design is having very strong influence during the solidification process, and the combination of all alloy precipitates during the solidifications. But to control the steel qualities in the industrial segment, because all these precipitates will create the lower ductility region in the steel semis, and which can lead to some defects attributes to the processes. But in case of vanadium additions, or the vanadium carbonitride or the others, because it is having the starting precipitates at the lower temperatures, so the most of the cases, the continuous caster is having the stressed regions are only overcome, and then it will start precipitating. So vanadium will have the added advantage towards the other, if I compare the other alloying. So improve the dot ductility behavior, the material, and it also saves a lot of the quality issues in the high tensile, high strain grades, because high strain. And another aspect I must tell about the control of the segregation during the solidification process is another very big aspect for maintaining the structural integrity, as well as the ultrasound cleanliness in the steel products, because that is very demanding right now in the current scenarios about the homogeneity and the segregation control in this thing. So the vanadium steels, we can minimize somewhat certain allowing, like the manganese, the solid solution strengthener, we can control, we can minimize down the manganese by adding the vanadium, where we need to have the very good amount of centerline continuity, centerline segregations to be maintained, or it has to be very good rating, has to be achieved in the macro etching, after the solidification process. So vanadium will act, a better manner, because that is the experience that we're talking about. When we are adding the vanadium, we can control the other solid solution strengthening a bit level during the alloy design aspect, to control the solidification pattern as well as the centerline conditions of the slabs. So that is very important aspect, because that is play an important role for any high strength products that we're going to supply to the market. Thank you, Manish.
Yeah, thank you, Sankadeep. Does any other panelist have to add on this before I move to the next audience question? Okay. I will move to an audience question on HSLA, that is high strength low alloy steel. To achieve high strength in HSLA steel sheet during cold rolling and annealing, which microalloying strategy will be more prominent? Only vanadium can be used singly or in combination to achieve high strength. Now, this question can be answered by all the panelists if they want to add. Maybe you can unmute yourself and answer.
Yeah, Manish, I will share our experience.
Yes.
So this particular question, exactly, we have done some experiments in our laboratory. For example, for producing ultrafine grain dual phase kind of a sheet, if you want to do, like the chemistry is also HSLA. We were successful in adopting these required properties in combination of vanadium and niobium. Okay. So we tried severe cold rolling and some warm rolling combinations, and then we got the best combination of strength and ductility for the HSLA sheet. So this we have done in the laboratory scale. This is my experience. Yes. Over to Manish.
Oh, okay.
Yes,
Debala?
I just want to add, yeah.
Yeah.
So actually, what is the challenge is during rolling or before that, the precipitation, if it can be avoided, then it's better. Because the thing is, if the precipitates are already present during rolling, then during annealing, there is a risk of coarsening. So instead of vanadium carbide, if we can vanadium nitride, it is better. But I just also want to add, as you asked the automotive steel, recently there has been a lot of interest on vanadium microalloy dual phase steel, because it is found that if the difference in hardness between ferrite and martensite can be reduced, then the whole expansion parameters and the other things can improve. And in strengthening the ferrite matrix, these vanadium precipitates can play a very important role. Some of the Japanese group you may find are working on this area. So this is one aspect where modern research is going on. But for that, rather than directly hitting to intercritical temperature, it may be better to go up to austenite and then come down and go for intercritical annealing, so that the precipitates can dissolve and the new precipitates form in ferrite. Second area I would like to add is, at least in research domain, you may have heard of nano high-ten steels. For hole expansion, as Senthil Kumaranji was mentioning, that for hole expansion we need a single phase matrix, preferably say fully ferrite matrix without any other second phase, with nanoprecipitates. So there, this vanadium microalloy fine precipitates, along with maybe moly or some expensive elements, if more research goes into it, then I think there is a prospect of developing a good hole expansion property, stretch flangeability and other thing, with very high strength, 800 MPa yield or something like that.
Yeah,
Yeah,
particularly
thank you.
that's what, like 40%, moving towards 40% for 780 kind of grades. I think
Yes.
vanadium
Right.
should play a role actually.
Yeah. Any other comment from any other panelist? Otherwise, we'll move to the second poll question. Let us run, Ramya, so that we get audience to participate, and I request audience to be patient with the announcement of lucky draw winners. So it is coming up soon. So first we'll run a poll question. Yes, here is the poll question on your screen. Do you think there is enough awareness about the benefits and challenges of using vanadium in steel among end users? There are three options. We'll close the poll question in another 15 seconds and then display the results. Okay, but more education is needed. And in fact, yes, majority say that there is awareness, of course, but more education and more such interactions are needed. So David, one of the key feedback is we should target more industry user sectors and academia as well as researchers to propagate this information about the advantages of using vanadium in high strength steel. Definitely. I will come to Senthil Kumaran as the end use industry sector of high strength steel. And your segment is going through the transformation in terms of fuel, as we know that e-mobility is big. Regulation, as we know that the Euro 6 and BS6, and then because it's always under transformation in terms of improvement in technology, lightweighting. So how do you see this sector shaping up in terms of usage of high strength steel for newer components within the changing landscape of mobility?
Yeah. So that's a very, very interesting question. And then we are in a kind of an inflection point. Like globally, people are migrating to electrification, whether it is hybrid or in terms of 100% plug-in born electric vehicles. So I think there is a big paradigm shift that is happening. Say, for example, if you really look at the driver for the lightweighting, the IC engine vehicles, the one of the biggest driver was emissions, right? You need to meet the CO2 emissions and all other emissions, whether it's now we are at BS6 and 6.2, we have migrated with real world emissions. That is the biggest driver. But if you really look at the electric vehicles, the biggest driver is range, right? That is absolutely not only in India, but in mature markets also, the range anxiety is there. So I think these are all the two drivers. But conventionally, if you really look at in the previous era, any new lightweighting technology using advanced lightweighting structures, whether it is steel or non-steel, composites, advanced aluminum alloys, a lot of honeycomb structures, foams, there is a gamut of material that is available for lightweighting. But if you really look at it, the options were limited because of the cost dynamics, right? The one of the most important thing I think everybody should understand is, say for example, in Indian context, say I wanted to reduce 1 kilogram of weight reduction, then my I was ready to pay say 150 rupees or 200 rupees. This is a premium somebody would pay for lightweighting, right? It could be steel or non-steel. Now the paradigm shift is happening like this. The biggest cost element in an electric vehicle is the battery system, battery pack, and the associated e-powertrain component. Say for example, I have a say 50 kilowatt battery pack for an X range. If I wanted to keep the same range or enhance the range, say for example, I wanted to make it really affordable, right? The penetration of these green vehicles, affordability is very important, right? Even a two-wheeler, cost a premium, you can see, and then fast cars, particularly with a higher range, the premium the end customer has to pay is higher if he really wanted to avoid the range anxiety. So what I'm trying to say is, say for example, if somebody wanted to reduce, if somebody is reduce 2 kilowatt hour battery pack, say for example, instead of 50 kilowatt battery pack, I am able to give it in 48 kilowatt per battery pack. The cost of lithium iron phosphate battery cells today is at around about hovering around 135 US dollars per kilowatt hour, right? So that means the cost, the premium what the OEMs can pay for lightweighting is really jumped multitude, right? Right from maybe $1 or $2 per kilogram. Now it is kilowatt $135, or about $170 is available if somebody is doing lightweighting to reduce that particular thing by just a 2 kilowatt battery system. So this is the new paradigm shift that is available, and I can see in our own range of vehicles and other things, there are a lot of impetus and things on. You are seeing Tesla, they have come with giga castings, right? There are aluminum, high strength aluminum, 6 series aluminum, 7 series aluminum has penetrated into the traditionally domains of trip steels or DP steels or hot stamped steel. They have penetrated. People like Sabic, they have penetrated in honeycomb structures for crash energy absorption. So what is happening now? There are absolutely new material technologies that are competing for a place in an automotive structure. That is happening right here in Indian market itself, right? So it's not like exotic some cars I'm talking about in an European or North American market. It is a mass market cars, electric cars, it is happening. So this is an important paradigm shift that is happening. And I think the researchers, the academia, and the RM manufacturers, I think they should be aware of this thing. It is there is an opportunity also in this new scenario. That is what I would like to tell this audience from the auto industry perspective, Manish.
Yeah, thank you. Thank you so much, Sanchil Kumaran. Since we are almost nearing the time allotted, I would request all the panelists. We heard the end use sectors uh, views and the road ahead. I would request we'll start with Sankadeep and then move to Sankaran, Debala, and Sudipta, and finally we'll have a summary note from Dr. Krothar, a quick 1 minute each on the road ahead and the the trends in vanadium steel in steel alloys.
Thank you, Mr. Manish. Regarding the vanadium additions, in order to ensure the sustainable development of the iron and steel in the iron and steel industry, the focus will be on the promoting the enhancement of the steel products and adjusting the structure of the steel products in the near future. So basically the aspect of weight reductions, in the high strength structures can minimize the welding consumables, as well as the weight reduction of the vehicles is also possible. So promoting the high strength structural steels or the high strength steels will definitely reduce the entire processing in the end users as well. So and in terms of the processing techniques, there are the in industry there are all advanced processing techniques are available, the equipments are available, so we can easily produce right now in India about the high strength steels and in the level of more than 700 MPa strengths, and that can easily be used in the automotive sector as well, and the high end structural segments.
Okay.
Thank you.
Yeah, thank you, Dr. Sankaran.
Yes, sir. There is a huge scope for these microalloy steels in the whatever we have studied in so far is only a plate form or sheet form. So we should enhance the scope for the much more all the dimensions like thicker, much thicker plates and much thicker sheets or much thicker, longer or complicated chemistries or without complicated chemistries. There is a scope to try on all these things with all the formability studies, which is not explored in our domain. So I think in future we should try all this combination. That's my view. Yeah, thank you. Over to Manish.
Oh, thank you. Thank you so much, Debala.
Yes, first of all, technically, I would like to say that sometime in India we have tendency of adding multiple microalloy elements together, but we have to be careful because sometimes what happens, one microalloy elements like titanium catches nitrogen, so there or carbon. So these elements do not remain for the vanadium to form precipitate. So we have to be a bit careful in using our spices in our cooking. Just because we have access to spices, we need not have to put all in our curry. So this is one technical point. And commercial point, I would also like to be interested about the use of microalloying in long products. For example, in TMT rebars, because some of you are coming from the industry. So I think you also can talk to your colleagues and see in construction bars, or Dr. Crowther already talked about rails, how the microalloy elements can be used effectively. And I also have done some survey and I found that it is important sometime to add these elements in the standards itself. Because in India, in some of the product standards, microalloy is still not permitted. So we may need to talk to the standardization agencies, governments, together, academia, industry, both, and introduce products like air-cooled microalloy rebars and things like that in a different market, but maybe a scope of using microalloying and lightweighting, which China is doing to a great extent. Yeah. Okay. Thank you.
Thank you so much. Thank you so much, Sudipta.
Yes, thank you, Manoj. So actually, I would like to bring the attention to stainless steel also. Like the question we have seen in Pradeep Rao asked about that, and in stainless steel also there are many high strength steel is being manufactured. Like recently we found that 450, 500 MPa strength in basically ferrite martensitic stainless steel, utility stainless steels. So, and also stainless steel river is being produced right now in India, and there is a standard government are trying to bring the stainless steel river in all marine area. I think 10 kilometer from the marine from the sea. So there is also, I think, scope of the addition and the use of vanadium there. Apart from the high strength, high toughness steel, particularly in low carbon variety, the stainless steel also, I think we have to explore that. Uh, that is from my side. Yeah.
Okay, very nice. Thank you, Sujit.
Mr.
Dr.
Manish,
Krothar?
Mr.
Yeah,
Manish, I just want to put one thing that regarding these long products, TMT, addition of vanadium in TMT bar in the industries are trying right now, because the specific cases like the seismic qualities, the TMT rebars where UTS by YS ratio is important to having the catastrophic failure during the seismic activity. And as you know that the vanadium is having the important characteristics like the hardenability of the martensite, the tame code that the facilities that the industries is having, so you can control the martensite transformation hardness during the tame code process. So the addition of control vanadium that can enhance the UTS by YS ratios. That is being done in industrial R&Ds. We have been trying for since long, and yeah, it will be pretty well successful that the making the super ductile TMT for the products like long products. The addition of vanadium will be a great, there'll be a great role on this. I must say thank you to Devlaji about highlighting this aspect, for adding the vanadium in the long products. Thank you.
There are some questions for Debala and others, and we'll collate those and we'll answer it offline for the paucity of time. But let us hear the summary from Dr. Krothar.
Thank you, Manish. I'd just like to concentrate on a couple of aspects. First of all, I'd like to highlight the versatility of vanadium-containing steels. We've heard from many of the panelists that they've got experience of using vanadium in automotive steels or forgings, a wide range of steels. And I've mentioned that vanadium can be used in high carbon rail steels, for example, in high carbon rod and wire, but also in low carbon steel. So it's a very versatile element. And this relates back to the fundamental solubility of vanadium carbides and vanadium nitrides. They're very soluble compared with niobium, titanium. The other aspects I'd like to mention are the consistency and robustness of vanadium-containing steels. We've heard from Debele, who's shown that you can get a very uniform grain size with vanadium-containing steels. And we've heard that vanadium-containing steels are relatively easy to cast. They're not prone to cracking because of their high hot ductility. Another aspect which I'd like to mention is the ease of rolling of these steels. Vanadium additions don't increase mill rolling loads, and that gives you benefits like you can perhaps roll a wider hot strip because you're not running into mill load limits. It reduces wear on rolling mill rolls, for example, so numerous benefits. So I'd like to finish off by saying, again, highlighting the versatility and the robustness and the manufacturing advantages that you can see with vanadium steels over a wide range of products. And finally, I'd just like to thank the panelists for their very knowledgeable contributions, and of course the audience for listening and asking some very interesting questions. So thank you from me to everyone.
Absolutely, and I propose vote of thanks, and then I would request my colleague Ramya to announce the lucky draw winners. So, David, thank you so much for joining us, Dr. Krothar, and thank you for partnering for creating this very interesting engagement initiative. I thank our knowledge partners, Technova, as well as AMTDC, IIT Madras, for being there with great support. And I thank all the panelists for joining us, taking time out of your busy schedule and sharing these useful insights, which I'm sure will go a long way in creating awareness and finding out, researching new areas for vanadium application in alloy steel. And I also request Ramya now to announce the winners of the lucky draw contest. Before that, if all the panelists have started their videos, then we can have a quick group photograph, and I request my colleagues at the back end to click group photograph. All of us are there? Yes. So remember, V for vanadium. Thank you. Over to you, Ramya, and also request, I must thank all the participants and audience for being very active and asking questions. Please follow us on LinkedIn. We will have a summary of these proceedings posted there, and the link will be shared with you during with an email, which will be sent to you by my colleagues. Thank you so much. Have a great evening, Ramya. Let us hear the names of the winners now.
Yes, Manish, thank you. For our wonderful audience who've been there throughout this webinar, I would like to congratulate the winners, the lucky draw winners. Our first winner is Mr. Santosh Kumar from SAIL. Many congratulations.
Steel Authority of India Limited. Okay, great.
Yes. Mr. Karthik Vasan from AMNS.
ArcelorMittal Nippon Steel. Great, congratulations.
Dr. Arun Kumar from NITK Suratkal.
Nice.
Indrajit De from Jindal Steels. Aarti
Congratulations.
Kumari from IIT Dhambar. And last but not the least, Mr. Amarjit Kumar from Bit Sindri. So these are our winners, and many congratulations to them.
So our team will reach out to the winners, and we need your addresses where the prize can be sent across to you. So we need your address with a PIN code. So congratulations again, and have a great evening, everyone. Thank you again to all the panelists. Thank you so much.
Thank you.
Thank you so much.
Thank you very much.
Bye-bye.
Goodbye.
Very much.